Okay, so I'm Will Q. I'm a staff scientist here at EMSL. I work primarily on characterization of complex mixtures, organic matter, obviously also things like metabolomics, using both mass spectrometry and nuclear resonance spectroscopy. But this morning I've been asked to talk a little bit about general overview of how you might characterize natural organic matter using high-res mass spec. So Renee did a great job this morning leading in with a lot of topics already. So the first few slides I've got, we can go through relatively quickly. But I do want to re-emphasize some points as we go through, just because they are really critical things you need to think about when you're doing your experiments. I will say my talk's going to go a little bit over what was planned in the schedule, so don't be alarmed when it gets to 10:30 and I'm still talking. So when we're talking about organic matter, especially this week, we're thinking about natural organic matter in soils, or soil organic matter specifically. And we know it plays huge roles in things like nutrient cycling and carbon sequestration. And we know it can be affected by things like droughts, floods, wildfire events, and all of these biogeochemical transformations come into play when we're thinking about not only the effects of these different, events on the soil, but also as probes for things that have happened in soils in the past. So there's a lot of reasons why we might be interested in organic matter in soils, but it's by no means the only organic matter that we're interested in. And so whilst obviously this week is focused on soils, I do want to mention a couple of other types of organic matter, just so you're aware that these techniques can be transferred to different research questions. So we also have a lot of organic matter in water, primarily in the form of dissolved organic matter. So this is, material that's in solution, but there's also obviously a lot of sediments in rivers. And we're not just thinking about rivers in this case, it can also be ocean environments, lakes, and so on. And these things are affected a lot by, agricultural runoff. We've changing climates. So for example, in Scotland, a lot of the water that we're drinking has increased levels of dissolved organic matter because the warming climate is changing the nature of peat bogs, which are causing more carbon to run off into the water system. That leads to things like nutrient changes or algal blooms. And so this very complex system is also something that a lot of our users are interested in studying. And then, of course, there's air. So this is a photo from a couple of years ago in Richland, where EMSL is located, and you can see this horrible thick smoke over the city. And this is the result of biomass burning events or wildfires. And these put huge amounts of organic matter into the atmosphere in the form of aerosols. And a lot of our researchers are interested in not only the origins of these organic matter in the air, but also what happens to them during their transport through the air, changing effects on exposure to radiation in the form of light or moisture, and the weathering events of these. And so there's a whole range of different types of organic matter that people are interested in. But as said, we're talking mostly about soils. This slide is really to re-emphasize a lot of what Renee had already covered. When we're thinking about organic matter, it's important not to talk in too specific terms when it is such a complex system derived from so many different origins. So obviously we have a lot of these complex biopolymers originating from plants, things like lignin, cellulose, but we also have microbes which exist in the soils. They produce enzymes which help to break down these complex biopolymers, but they also have their own metabolic profiles. They also exude lipids and proteins into the soils, as do the plants themselves. So there's a lot of different sources for biological carbon in organic matter. We've also got a lot of inorganic systems going on. We have all of these minerals which play huge and complicated roles. You can have absorption of organic matter to the mineral surfaces. They can accelerate reactions and change the chemistry of the organic matter just by their presence. And there's obviously a whole world of different types of minerals. And then, of course, there's physical effects. And so there's things like photodegradation, which is one of the nice examples at the end of Renee's talk this morning, but also changing levels of moisture and humidity, changing temperatures, oxidation and exposure to oxygen can also change the nature of organic matter in our system quite a lot. So there's a lot of different things going on, which does make this a very complicated system. So as you all know, there are a number of different types of soils. There's ones which are very rich in minerals. There's ones which have been quite affected by anthropogenic effects like agricultural soils. There's also ones which are extremely rich in carbon like peat bogs. And their composition is quite complex and rich. But the section we're really interested in is organic matter. And again, there's a whole range of different techniques that you can do. You can look at elemental level characterization, looking at things like total organic carbon, nitrogen, and so on. Or you can do molecular level characterization, like nuclear magnetic resonance or mass spectrometry. There's mass spectrometry, which we're going to talk about this morning. with the real question of, organic matter is highly complex and heterogeneous, and it comprises of thousands of different molecules. So how can we use mass spectrometry to help us understand it? So in the next section, I want to give a very sort of general overview of the typical workflow one might undertake doing a project looking at soil organic matter. And then I'm going to pick at some of these specific areas and talk a little bit more about some of the choices that are made, some of the practical aspects and considerations, really building on a lot of what we learned this morning. So the first thing you need to do is obviously identify a site. You need to get your permissions and your permits so that you can go there, do your sampling and collect your soils. You might take them back to the lab, do some homogenization, do some fractionation perhaps, and get your soil samples. Then, of course, we need to extract the organic matter from the soil matrix, typically with the liquid extraction. As noted earlier, obviously, we have to clean up the samples most of the time. So this is a solid phase extraction manifold. This is one of the most common ways of cleaning up our samples. Then we perform our mass spectrometry analysis. This is a photo of EMSL's flagship mass spectrometer, the 21 Tesla FTICR instrument, one of only two in the world. And so we use this for a lot of our highly complex samples. And then the sort of data that we get out at the end of it looks something like this. So this is a really complex mass spectrum showing thousands of features across a wide mass range. And so the next section is just, how do we actually do some of these steps? So as noted by Renee, sample preparation is really a critical step. You need to consider whether or not you're going to dry your samples, and if so, if you're just going to air dry them or lyophilize them, or if you want to keep them fresh, noting that any of these choices will have effects on the soil chemistry, whether you choose to store them in an inert atmosphere or in air, and whether you choose to store them at ambient conditions on a bench, or if you want to store them frozen at -80. Whatever you do, it will have an impact. And then what we typically recommend for our users is that the soils obviously need to be homogenized as far as possible. Ideally, you want to do some sort of fractionation of them, because there's different chemistries on the different size fractions of these soil particles. And one really key step is to make sure you remove any large detritus. So make sure there's no big leaves in there, there's no sticks, there's no rocks, because those are obviously not the soil that we're interested in characterizing, and would throw off any of our quantitative sample prep. Most of the mass spectrometry that we do is using liquid state samples, and soil is not a liquid. So the first thing that we often have to do is get our sample into the liquid state. And most of the time, there's only a handful of different extraction protocols we might use, but we have to make sure that we pick the right one for the question at hand. So we have water extractions, which can be done at various temperatures, depending again on the system. You might want to use hot water or chilled. There's organic solvents you can use like methanol, chloroform, or hexane. And then the order in which you do extractions can matter as well. So you may choose to do a sequential protocol where you first do an extraction with water, and then you take the soil that's left and you do another extraction using methanol, and then follow that with a chloroform extraction. Or you may choose to do concurrent protocols. So PNNL has an extraction protocol called the MPlex extraction, which in many ways is a modified Fulch or Bly type extraction, which yields for us multiple analyzed fractions in one extraction. And this uses 3 solvents at once to produce these different fractions for us. A few notes here, water extractions are really good for getting bioavailable polar molecules. They tend to get anything that's, freely floating around in the soil, so extracellular compounds. But remember that if you've not sterilized your soil and you leave it in water for 2 hours to extract it, any microbes that are there may do some more activity over time. Alternatively, if you use an organic solvent like chloroform or something, just remember some basic chemistry that like dissolves like. So if you use a very non-polar solvent like chloroform, you're going to extract non-polar molecules like lipids. These solvents can also arrest any biological activity, and they can lyse cells. So if you want to get access to any intracellular compounds inside the microbes inside your soils, some of these solvents might be more appropriate. Sequential extractions give you more control over whether you're getting intra or extracellular compounds, but of course the microbial activity can persist. But if you go for this concurrent extraction, you get multiple fractions at once, which can serve pipelines like proteomics, lipidomics, metabolomics, and our organic matter workflows all at once. But remember that you're lysing the cells, you get all of the fractions containing all of these intra and extracellular compounds, which depending on the amount of microbes in your soil may or may not be a huge issue. So as I noted, there's a bunch of biases and considerations to think about here. You've got your microbial activity, intra and extracellular compounds, but there's also mineral-associated organic matter, which I haven't really mentioned here. A lot of it's quite recalcitrant, doesn't get extracted readily with the basic solvents we've already talked about. And so there's a lot of other extractions using things like sodium hydroxide or hydrofluoric acid, which really try and address this and extract more of this organic matter. But generally, this is quite problematic when we do mass spectrometry. And there's variables like how long is the extraction, what temperature do you do it at, do you expose it to light and air during this? And then there's also the ratios of sample to solvent, which tend to depend on the amount of carbon that's in your soil. And there's also things like what ratio of solvents you use. So when you do an extraction like an Mplex or a Fulch, it's actually critical, the ratio of the different solvents you use. And then one key note here, it's fairly obvious, but no extraction will ever get you everything. No extraction would ever get 100% of the carbon removed, especially when you think about water extractions, because if water removed most of the organic matter, there wouldn't be any organic matter in soil. So we also note that sample soils contain a lot more than just organic matter. Minerals, which in some terms is a catch-all for things like trace metals, salts, and of course, geological things like minerals themselves. The problem is a lot of these compounds are also soluble in the chosen extraction process. A lot of these, free metals or low molecular weight salts easily solubilize. And some extractions even produce more. So if we use things like sodium hydroxide, we're adding a bunch more sodium cations to our sample, which we don't necessarily want. Especially when we're doing direct infusion mass spectrometry, these things are quite problematic if we don't address them. So as noted before, solid phase extraction is the most common protocol people tend to use. It's a type of offline chromatography or separation. And the basic idea is that your sample, which is a liquid, goes into these plastic cartridges, and the analytes of interest, the organic matter, sticks to these little brown pellets, whilst all of the salts and metals that you don't want don't stick to it and just wash straight through it. We rinse it a few times with some clean water, and then we use methanol to unstick our analytes of interest from this sorbent material and elute them into clean vials. So this is a really straightforward protocol which works really nicely at cleaning up our samples. The PPL protocol, which the majority of the community seems to use, comes from this 2008 paper from Dittmar. And it was originally about marine samples. And so what was really nice is that it worked at removing huge levels of salt, as you'd expect in an ocean. It also works for really large volumes, so they could do up to 50 liters potentially. And it removes these salts and it recovers a high level of organic carbon. But it's not perfect. We tend to lose the most polar small molecules. So things like sugars and amino acids are very, very poorly retained and tend to be lost in this protocol. It's not optimal if you're interested in nitrogen and phosphorus compounds potentially. It was optimized based on organic carbon recovery. And one of the last steps is to actually wash it with this low concentration of hydrochloric acid, which can leave some amount of chlorides in our final product, which is not necessarily desirable. This is a mass spectrum example showing you the difference of analyzing the raw extract of in this case, it was Elliott soil done with a simple water extraction versus the SPE version of the exact same extraction. And you can see that this narrow region of the mass spectrum looks completely different. And so in the top case, the most dominant feature at this nominal mass is some sugar-like compound, some disaccharide type compound. But after we do SPE, we get a slightly richer looking region of spectrum, but completely different features there. And so what's going on here is SPE is really changing what we see. So this is these Van Crevelen diagrams, which you may have seen before. This is the same data as on the previous slide, but visualized in this two-dimensional scatter plot. And I'll go into it a bit more towards the end, but the key takeaway here is twofold. One, these look extremely different. And two, without SPE, so in the top left panel, there's actually far, far fewer features. There's maybe only 2,000 features detected. Whereas if we do the SPE protocol, we get 5 times as many features detected. So you have this big compromise decision to make between, do you want certain compounds, but very, very few of them, or do you want a richer spectrum with more information in it? once you've decided on all of those things, it's finally time to do the mass spectrometry. So recognizing that most of you may not be mass spectrometrists, but you may have heard of some different types. You might have heard of things like triple quads or TOFs. It's important to know that all of these different technologies have their own advantages and disadvantages, especially when it comes to things like cost, sensitivity, and complexity. But when we're talking about complex mixtures like organic matter, FTICR is the gold standard. There isn't another technology which can achieve the same levels of resolution as FTICR. And so in EMSL's case, we're extremely fortunate to have one of the two in the world 21 Tesla FTICR instruments. So what you're seeing here in this big cylinder is a superconducting magnet, a bit like an MRI scanner, except it's roughly 10 to 20 times stronger than an MRI magnet. It's also substantially larger and quite expensive. And so a very specialized piece of kit. But with this high magnetic field, we're able to achieve the best possible performance. What does a mass spectrum look like? If you've not seen one before, this is a very typical directed fusion mass spectrum of organic matter acquired in negative mode, electrospray ionization. And you can see that it's quite rich. There's a lot of features extending over a wide mass range from about 200 to 800 mass to charge units. And it's this sort of skewed normal distribution that's very telltale of a lot of heavily degraded organic matter. If we zoom into a narrow region of this mass spectrum, you can see that we now have a series of features at each nominal mass. So it's 376 m/z, it's 378 m/z, and so on and so forth. And there's also this interesting pattern of high and low features alternating. And what this tells us is that we've got a lot of what we call monoisotopic features, and then their carbon-13 isotopolog peaks here. And so this tells us a little bit about the data. It tells us that these species are singly charged because there's a 1 mass per unit difference between them. And it tells us about something about the type of chemistry we might be observing. If we zoom in further to just a 2 mass to charge unit window, you can see that we have quite a rich spectrum going on at each of these masses, and then a big gap between them, which is very typical again for our organic matter. And we've got all of these peaks, maybe 6 or so intense ones at 379. And it transpires that they're all paired up with their carbon isotope, isotopolog ions at plus 1.0033 mass to charge units. So you can see here, we're measuring in the real world masses with really, really high precision and accuracy, and mass differences with really high precision and accuracy. And so this is one of the true strengths of FTICR. Now, if we zoom in further to just a single one of these nominal masses, you can see that at the nominal mass 379, there are half a dozen or so intense features, and then a number of less intense features in the spectrum. And so despite the fact that we have a single mass here, there's actually numbers of different ions. And so these ions would not be resolved on a lower resolution analyzer. If you had something like an ion trap, you would just see one hump for this whole mass. But what we see again are some typical repeating distances between our ions, which is indicative of replacing a CH4 with an oxygen 16. Because despite the fact that both of those weigh nominally 16 daltons, their exact mass difference is actually 36.4 millidaltons. With the ability to measure such high precision masses with such high accuracy, we're able to infer molecular formula for each of these peaks. And so in this case, you can see we get something like C17H16O10, which tells us something about the chemistry, tells us something about the composition of this molecule, but it's really important to note it doesn't tell us the structure. It just tells us a molecular formula. If you cross-reference this formula with a chemical database, you see that there's at least 8, probably a lot more, different isomers, both structural isomers and stereoisomers, and we're not resolving either of those. With direct infusion mass spec, each of these peaks may be one structure or it may be many structures, and it's just not possible to tell with this technique on its own. That being said, many of these structures are quite similar. You've got this aromatic moiety and a sugar. You've got some glycosidic formation going on here. So this may be something that is, a secondary metabolite or some sort of lignin-derived compound. And that's true for maybe 6 out of the 8 molecules here. So you could make some inferences about the probability of certain types of structures. But there are other structures that could be possible here, like this one here, which doesn't have a sugar in it at all. So you really have to be careful when you're inferring any sort of property from a molecular formula that you don't go too far. Now, all mass spec starts with ionization, because in mass spectrometry, we're measuring ions, these charged particles. And so what we have to do in the first step is convert our analyte molecules, in this case, they're in the liquid phase, to gas phase ions. And the most common way in which people do that for this sort of characterization is using a technique known as electrospray ionization. This technique is really good because it is very soft, which means that it yields minimal fragmentation. Most of the ions that we see are essentially molecular ions and are telling us things about the intact structures of molecules in the not structures, compositions of molecules in our samples. And it's really applicable to a wide range of molecules across size. It's also pretty ubiquitous ionization to source. Most labs have it, which means that everyone can do this sort of measurement, provided you have the mass analyzer, of course. That said, it has some disadvantages. It is not salt tolerant as well. So we've mentioned this a few times, but the main limitation is that when you have a lot of salt in your sample, it can cause ion suppression, which yields reduced sensitivity. The easy way to imagine this is that you can only have X number of charges going on at any time. If you have a lot of salts, a lot of sodium ions, for example, or a lot of chloride ions, those things are so easily charged that they can take all of the free charge you have, for lack of a better term. They can also form a lot of adduct ions, which basically means that one molecule can become many different ions, which can complicate your spectra and make it seem more diverse than it may necessarily be. When we do ESI for organic matter, we tend to use negative mode. It works best most of the time. And in this case, we're forming negatively charged ions. And the primary mechanism for this is the loss of an acidic proton. So if you have a carboxylic acid group or an alcohol group that can be stabilized by the overall structure of the molecule, you can form this M minus H ion pretty readily. And then you've got your nice ion for you to analyze. You can also form chloride adducts sometimes. If we do positive mode, which is less common, but it is done, the idea is that it might ionize some basic nitrogen compounds. But unfortunately, more commonly, you still just get majority of these CHO containing compounds. And you can either form these M plus H ions, where the molecule has gained a free proton, or it can form an adduct ion with sodium or potassium, for example. So you can see here how, if you do positive mode, you could potentially form 3 ions for the same molecule, which could make your spectrum much more complicated than you wish. I put this slide in just so you get a grasp for some of the numbers that we're thinking about. So a typical workflow that we might do in the lab, we take our organic matter sample and we dissolve it in methanol at a concentration somewhere between 0.01 milligrams per milliliter up to 0.1 mg per mil. You can go slightly higher or slightly lower depending on your instrument and your sample, but these are good ranges. And then for mass spec, we typically only need 100 microliters of sample or so. So we're talking high sensitivity and low volume sample requirements. We might infuse it at a flow rate of about 3 microliters a minute, giving us the ability to record data for about 30 minutes or so. And the overall experiment takes 5 to 15 minutes per measurement, shall we say. So it's not the fastest technique by any stretch. It is actually quite a slow mass spectrometry technique. And then, of course, you have to make sure you clean and flush before running the next sample, because mass spec is a contact analysis. And so if you don't sufficiently clean, you get a lot of carryover and contamination between samples, which you'd want to avoid. So for the next few slides, I prepared a series of animations about how FTICR works. I hope these animations will translate well over Zoom. And so at first you have your ionization source. So this is a photograph of the Bruker ESI source we have on one of our FTICRs. As you can see, this is on our 12 Tesla instrument. And the idea is that your sample is loaded into a syringe over here, and then it is it's infused into the sprayer or the ESI source through a narrow silica line as such. So we got this little animation going. And then in this photograph, the spray shield door is open, which obviously is only used for cleaning or flushing samples. But I've got it here so you can see more easily what's happening. The sample goes through this sprayer and is nebulized into the gas phase or aerosolized, and you get all of these small little gas molecules. If we zoom in on that region, you can see that on the right-hand side is the Bruker source, and on the left-hand side is an example of the thermo-ESI interface. And you can see the basic idea is that you've got this fine-tipped point at the end of your sprayer. Your sample is nebulized through there into this gas phase, and then it goes from the atmospheric pressure, where we are, into the vacuum chamber of the mass spectrometer through this very narrow capillary opening. You also notice on this instrument, there's a lot of brown residue here. That is because the sample, the stuff that doesn't go into the instrument sticks to the front of the instrument. So we have to clean this quite regularly to avoid too much contamination. Now, for the next few slides, I've made a very simplified instrument schematic, but so you can put it in context, I've got a photograph of our real 12 Tesla instrument in the lab. In this case, the instrument is what we call rolled out. This titanium flight tube here actually goes all the way into the magnet, but we roll it out for maintenance. And then everything we have over here on the right-hand side is the cart, as we call it, or the spectrometer. It contains all of the electronics, the pumps, all of that instrument is basically the mass spectrometer. And then on the left-hand side is the magnet. And so that's just a superconducting magnet. It doesn't really do anything beyond be a magnet. And so hopefully that translates to the schematic on the top. And so the general idea of the experiment is that ions are generated at our electrospray source. And these are my little stars, and they are transmitted from atmospheric pressure into the vacuum chamber through this little capillary, where they go to regions of increasingly high vacuum or low pressure. And they're focused by various different ion optics elements. In the next step, these ions are transmitted through a mass filtering quadrupole before entering a collision cell. So we use the quadrupole to help us get rid of any ions we don't want, things that are too small or too big or outside of our range of interest. And we accumulate a packet of ions in the collision cell because we need to make sure we have enough ions to make a measurement. This is a sort of batch measurement. It's not a continuous measurement. Despite the fact the ions are continuously flushing into the instrument, we only make measurements in discrete intervals. So these ions pass through the quadrupole. In this case, we lose one of those ions, and the rest of them are accumulated here for a specific amount of time. If you want to do any sort of tandem mass spectrometry or MSMS experiments, they would be performed in the collision cell here as well. Now, once the cell is full and we want to start our measurement, we have to eject them from the collision cell through the flight tube into the ICR cell, which is in the center of the magnetic field. And so the really important thing to note is that not all of the ions travel at the same speed. So some of them get there really quick, some of them get there slower. Basically, small molecules fly faster. And so we have the ICR cell open for a certain period of time known as the time of flight. And it's about a millisecond, and it's how long we allow ions to transfer from here to the ICR cell. And on the 21 Tesla instrument, that distance is 2 meters. It's a really quite a long distance. They do travel very, very quickly. Once the ions are inside the ICR cell, remember they're inside both a really high magnetic field and an ultra high vacuum. But in this magnetic field, they begin to undergo what's known as cyclotron motion. They spin around the center of the cell at a frequency which is dependent upon their mass to charge ratio. When they have a lower mass, they go faster. When they have a higher charge, they go faster. And so this can be kind of a difficult measurement to conceptualize. So I've got a couple more animations which hopefully make it seem slightly more obvious. Now, do recognize these are big simplifications. It's actually quite complicated physics. But at the start of the experiment, the ions are just sitting in the center of the cell, maybe orbiting a 1 millimeter radius, very, very small. And so that's too far away from our detection electrodes to really be seen. So instead, what we do is we apply an on-resonance radio frequency pulse, which excites them to expand their radius. So this pulse goes in, and now they have a much higher radius. And at this point, they're now close enough to the detection electrodes that they can induce a current. This is just, charged particle moving induces current. This is a view from another angle. So this is through the magnetic field z-axis rather than a side-on viewpoint, but it's the same animation again, just showing you that again, at the start, the ions are in the center, they're spinning around a very small range. We apply a radio frequency pulse to those and it excites their orbit quite big. So now they're much closer to those detection electrodes. And then once we have them at this orbit that we want, they continue to stay at that orbit and they pass through and they continue going round and round. And so what we can actually do here is now record the signal that they induce on these detectors. And so as they spin around, they induce a signal on our detection electrodes, something like this. And you'll notice as well, they spin at different rates. As I've said before, their frequency of motion is proportional to their mass to charge ratio, or the first approximation to their mass. We don't, of course, record the 3 separate signals. We record one signal that might look something a bit more complicated like this. And so we need to deconvolute this signal so we can actually understand its constituent parts. And the way that we do this is using a Fourier transform. And so we take our signal, which is many components. We apply a Fourier transform, which, don't worry, the maths is complicated, but computers do it all automatically. And that Fourier transform takes us from a time domain signal to the frequency domain. And then once we are in the frequency domain, we can apply a relatively straightforward mass calibration, which converts the frequencies to the mass to charge domain. We apply this, and then finally, we get our mass spectrum. So that is a very, very whistle-stop tour of how FTICR experiments work. It's obviously a lot more nuanced than that. But what I hope to get across is that there's a lot of choices and parameters and optimization that needs to be made there. And it's definitely not the most simple mass spectrometry that you can do. But it is the only one that can achieve such high resolutions. Now, I showed you very, very simple circles as the cells. In actual fact, these ICR cells can be quite exotic and elegant in their design. I have photos of 3 of the different cells that we have here at PNNL. So we have a couple of commercial ones on the top, this very small infinity cell. This is an older style, and then versus these 2 much more modern geometries, which are much longer, you might notice. And so one of the advantages of being longer is that you can put more ions in there, so it can improve your sensitivity. There's also a number of other improvements. The key takeaways, though, for FTICR is that we're measuring the cyclotron motion of ions in a very strong magnetic field and in an ultra-high vacuum. We're talking 10 to the minus 10 millibar, which is, you know, on the pretty close to the vacuum in space. It's really, really high vacuums. It's a Fourier transform technique, so it's very high resolution, and it's multiplexed, which means we're measuring all of our ions at once. But it requires careful control and optimization of the whole instrument if you want to gain high quality spectra. Now, a couple of concepts that I want to just briefly mention. I've talked about this a little bit before, but the time domain signal, the transient that we record, which is also known as a free induction decay, the length of this transient here in the time domain dictates the resolution that we can achieve in the frequency or mass domain. If it's a very short recording, we get a very wide peak, a very low resolution. However, if we record for much longer, our peak becomes much narrower. So there's a trade-off here between how quick our measurements are and how high resolution our measurements are. Similarly, if we want to improve sensitivity, as it is a Fourier transform technique, we can do signal averaging, where we record the same measurement again and again and again, and add those signals together. And if we do this, the signal to noise can increase by proportionally to the square root of the number of scans. And so if we record 4 times as many scans or transients, we can get a 2-fold improvement in signal to noise. So this again means that, yeah, we can make high resolution and high sensitivity measurements, but that can take time. Another concept which you might hear about a lot is parts per million when we're talking about mass errors or mass differences. And the reason why we choose to use this is because often the mass differences we're describing are very, very small in absolute terms. So you see here, for example, this mass difference between these 2 peaks is 0.004 mass to charge units. So in this case, it's about 4 millidaltons apart, which is really, really small. But if we put it in ppm, it's much easier to describe. It's 10 ppm at 400 m/z. You can see just how high resolution mass spectra or FTICR can be when we're talking about these features down here. So we have two peaks here that are barely resolved. There's maybe a 10% resolution between the two of those, but their mass difference is less than 1 millidalton. It's just over the mass of an electron. So this is a really, really minuscule difference between peaks. But FTICR is high enough resolution to actually detect and resolve those features. The other thing that you've heard about, and you'll hear a little bit more about from Yuri, I'm sure, is about exact masses. And so this is really how you go from a mass measurement with high precision and accuracy to an elemental formula. And it all relies on the fact that all isotopes have a unique exact mass. And so the exact mass is this value here. Whereas before you might think, well, hydrogen weighs 1, carbon weighs 12, nitrogen weighs 14. In actual fact, their exact mass is slightly off from those values in most cases, except for carbon-12. The other thing to note is that most most isotopes have what's called a negative mass defect. And so this means the value is below the integer mass versus the handful of isotopes at the top, which have a positive mass defect. And we use the same terminology when describing a peak in a mass spectrum as well, if it's above or below the integer mass. And the final thing to note is that all of these isotopes have known natural abundances. And with these natural abundances, we can predict what we would expect to see in our mass spectrum. So I mentioned before that you can observe these carbon-13 isotopes, but you notice it's at 1.1%. So we can actually look at the ratio of these different peaks in our spectrum and compare them to what we expect, and use all of those pieces of information together to give us some idea about the molecular formula composition of that peak. Now, I mentioned before that we want good quality data, and it's pretty easy to make bad data. So this is an example of a organic matter sample that we were analyzing in one of our instruments. Contemporaneous spectra, just the settings were not optimal on the first time we tried to make the measurement. And in the top, you see these peaks, which at the face of it might not look too bad, but in actual fact, they are basically unusable data at this point. These peaks are significantly broader than they should be. There's slight shouldering, there's slight peak splitting. If we improve our measurement, we actually get these much, much better looking line shapes. And what we're really aiming for are sharp, narrow, symmetrical features. And this can be caused by a whole bunch of different things. In this particular instance, it was just caused by unstable ion populations. If we co-add 200 scans together, we need to make sure that those 200 scans are consistent. And in this case, there was some slight inconsistency between them, which we resolved. Now, what do we do with the data? I don't want to go too much into this because that's some of what Yuri will talk about, and then tomorrow's sessions. But on the face of it, there's a few things you can do. We've got these molecular formulas, so we can calculate stoichiometric properties. So things like double bond equivalence, aromaticity index, or nominal oxidation state of carbon can tell you things about the average property of the molecule inferred from its molecular formula. Remembering, of course, that it's an average of a molecule and it doesn't necessarily capture all of the nuances between isomeric structures. So for example, when we talk about aromaticity index, it isn't necessarily saying if the whole molecule is aromatic. You could imagine an aromatic structure bonded to a sugar. And in that case, maybe it's 50% aromatic. And so aromaticity index can represent properties like that. The other thing that comes up a lot is the Van Crevelen diagram. And so I want to take a couple of minutes just to go through the origin of it and then how people are reusing it today. So the first Van Crevelen diagram, eponymously named by Dirk Van Crevelen in 1950, was used to study bulk fuel samples. So he was interested in things like coals and wood and understanding about their composition on a bulk elemental ratio level. So what he did was he determined the oxygen to carbon ratio and hydrogen to carbon ratio of these bulk materials and plots them in this two-dimensional space. And there's a couple of main things to take away from what he was able to achieve. Bearing in mind, this is in 1950, long before we had the high resolution molecular level techniques we have today. He was able to infer that depending on these lines through these diagrams, you can pull apart whether or not there's certain processes or transformations taking place. Things like dehydration or hydration may be a diagonal feature. Hydrogenation or dehydrogenation may be a vertical line, for example. The other thing that he was able to pull apart was you could use this to infer things about the composition of the molecules based on where they fall in space. And so in this case, he determined cellulose is up here in the top right with roughly a 1-to-1 oxygen to carbon ratio, and lignin is somewhere in the middle at maybe a 0.5 oxygen to carbon ratio. And then when he measured wood, so a bulk wood sample, stuck it on the plot, it came about here. And so from this, he was able to estimate that wood was roughly 2/3 cellulose and 1/3 lignin based on the relative contributions of these parts. Obviously, in that case, cellulose was actually hemicellulose as well, but this is actually a pretty accurate number for the real composition of wood based on a fairly trivial mechanism. Anyway, in 2003, the Van Crevelen diagram was repurposed for ultra-high resolution mass spec. And so what they did was, instead of looking at bulk sample elemental ratios, looking at molecular formula atomic ratios. And in this case, you now have thousands of data points in the scatter plot representing the thousands of mass spec peaks that you had originally. Again, plotted according to their oxygen to carbon ratio and hydrogen to carbon ratio, where each point in this plot is from the mass spectrum. Again, we have these diagonal lines and vertical lines that can be used to infer things about the transformations that are occurring in the sample. The other thing that a lot of people like to do is infer based on the region in the plot what type of chemistries those molecular formulas might have. So again, if it's up in the top right corner, you might assume it's a carbohydrate or cellulose. If it's up in the top left, you might assume it's a lipid or a fatty acid, and so on and so forth, depending on how you space out this diagram. Now, over the last 19 years or so, the Van Crevelen diagram has exploded, and everybody is using it in their complex mixture analysis. And there's been a lot of discussion about the appropriateness of some of these inferences. And so there's actually quite an interesting paper from P&L about 4 years ago now, where they revisited this concept in this diagram and really expanded on some of the definitions, some of the calculations you could do, and really trying to embrace the idea that these regions, like you might have defined previously on the left, they're not cleanly resolved. And in actual fact, there's a lot of overlap and gray and ambiguity when we're talking about where molecules fall in these diagrams. So when you see these diagrams, they can be very useful, but they're by no means exhaustive or completely comprehensive, and you have to be careful with them. So all of that to say was primarily focused on direct infusion, electrospray ionization. That's not the only technique that exists. Just as an example, it's also possible to do laser desorption ionization. So this is a solid phase technique where we analyze the soils directly. We stick them onto a little target, stick them inside the mass spectrometer, and a laser fires at the soil samples and directly desorbs and ionizes molecules from the surface. Big challenge in homogenizing these samples, big challenge in making sure that you don't have detritus in them. These are microscopic particles, but they're still big enough to cause issues. But the real advantage, theoretically at least, is that you can do LDI without having to do an extraction step, without having to clean up the sample. And so you can analyze the whole soil intact, in essence. What we've discovered is that you actually cover a completely different type of chemistry. So this is an example of an agricultural soil that was maybe 4% carbon. And in green, we have the LDI mass spectrum, which had about 9,000 annotations. And in orange in the bottom, we have the traditional electrospray ionization workflow, which had roughly the same number of annotations. But when you zoom in to the individual masses, you notice that they are completely different spectra. And if we plot that on a Van Crevelen diagram, you see that we're covering completely different regions of chemical space with these two different ionization techniques. So again, just like SPE completely changes what you see, your choice of ionization source can fundamentally change what you observe. Where LDI tends to produce these more condensed aromatic ions versus ESI forming more of these slightly more aliphatic or saturated species. You might also wonder why we're always doing direct infusion. There's two main reasons. One is that liquid chromatography, any chromatography, is just not good enough for these ultra complex mixtures. Nobody has yet solved the problem of getting perfect separation of complex mixtures with chromatography, especially not the organic matter. And so what you tend to observe in the chromatogram is these broad humps. So even last year, 2 papers came out using LC coupled to ICR, but in both cases, they observed just 3 broad humps across their chromatogram. And it gives you some advantages. You get more coverage, you might get less ion suppression effects. You might be able to do the analysis without SPE beforehand, all that sort of stuff. But the other challenge is the data analysis becomes much more complicated. Instead of one spectrum, you've now got hundreds or thousands of spectra in your LC data set. And then finally, data analysis. I'm not going to touch on this. It's Yuri's realm and then tomorrow's, but just to say that there are a lot of tools out there for data analysis. Whilst, you know, the big names, maybe vendor tools or proprietary tools, the majority of what we do day to day actually uses open source tools, things like CoreMS, which was developed here at EMSL, or some tools that have come from other labs like MFSINR. With that, I want to thank you, take any questions, and then just for the sake of completion, I put together a slide with some references. If you're really interested, I suggest you check some of these things out. If you just want a good review and overview, I suggest you have a look at these two from Mass Spec Reviews that came out relatively recently. Definitely good resources if you want to learn more. Thank you.
All right, thank you. That was great. So we have like a couple questions on the chat here, so I'm gonna start reading some for you. So we have one from Becca, is with ultra high resolution mass spec, does this just show presence, absence of molecules, or we can obtain actual abundances?
That is an excellent question that I somehow completely forgot to include in this talk. It's very complicated is the answer, but in short, you should be very, very careful if you try to infer from the abundance or the signal intensity. The signal intensity is proportional to the ions in the trap, but those ions in the trap are heavily affected by every other choice you've made. So how you tune the instrument, what ionization source you've got on there, if there's competitive ionization, all of those things change what you see. It isn't just what was in your soil at the beginning. So generally, we recommend people do presence absence type comparisons. There are some efforts in the work to try and understand the limitations and the possibilities of using abundances slightly more quantitatively, but as a rule of thumb, just don't if you can.
Okay, next one. Hi, William. Thank you so much for your great presentation. Do you have any suggestions on extracting and measuring the composition, including potential quantity and volume of organic acids and amino acids, soil samples? Are these methods of extraction affected by soil pH?
That's an excellent question. The problem in giving answers to questions like that is that soils are so different. And so we have definitely had users who want to extract organic acids from samples and us to analyze them. But it becomes a little bit exploratory in every project until you have a feeling for how much organic acids or amino acids might be in the sample. That said, they're generally going to be soluble in things like water, maybe water methanol as a mixture. So that would be where I would start. There's a number of protocols for targeted analysis. Important to remember that everything we've talked about right so far is really an untargeted characterization. If you are interested in specific chemistry, specific molecules, you could start to look at, existing LC protocols for organic acid characterization and just work in that direction. But as for like amounts of soil, amounts of sample, it's essentially impossible to answer without knowing your soil sample.
Complicated one. So the next one, what database do you use to identify, potentially annotate the mass features?
So because we could potentially detect thousands and thousands of things, but we're doing it essentially on exact masses alone, what most of the community does is use computational databases. So what we do is we generate all possible molecular formula based on certain physical constraints. So we know as chemists that there's only so many combinations of carbon, hydrogen, oxygen that you can feasibly put together. You're not going to have a molecule with 10 oxygens and 1 carbon. And so with simple rules like that, the ratios of expected carbon, oxygen, hydrogen, oxygen, nitrogen, carbon, things like that, we can start to pull together a database. And so that's how tools like CoreMS, tools like Formularity work, is by pre-generating a big database of possible molecular formula. These are entirely in silico, entirely synthetic molecular formula, and then cross-checking the masses we measure with the masses in the database.
That's a good question. I'll talk more about that during my presentation as well. I'm going to skip that one, but for the data processing part of the mass spectrum, how you determine if the poorly resolved peaks are actually signals and not noise or mass deviation? What threshold value would you suggest?
So in the case of that bad spectrum I showed up front, what's nice about that sort of data, nice in a very, ironic way, is that for that particular artifact, it tends to be across the whole mass spectrum. So if all of your peaks look bad, it's a pretty good idea that your data is bad rather than you're just not resolving features. That said, there are instances where you might have some regions of the mass spectrum look bad, and it's kind of difficult in abstract to know if it's a unresolved feature or if it's a bad peak shape. And so unfortunately, in those weird edge cases, the only solution is to go back to the instrument and make more measurements to confirm what you're seeing.
Cool. I think you have time for one more question. And I see there's more questions popping up. So after that one, please go back, refer to the Discord. Maybe we'll be able to answer more questions after the time. So the last one is, who will be the first person in EMSL to contact to discuss the possible facilities of availability for the research questions and to write a proposal?
So what I strongly suggest you do is check out the EMSL website and have a look at the science areas and the integrated research platforms that we have, and get in touch with either the science area lead associated with the question you're really asking, or the IRP lead, the integrated research platform lead. We have different structures here depending on if the question is more biogeochemical or if the question is more biological and metabolomic, for example. And so reach out to those contacts and they will direct you to the appropriate instrument scientists as necessary.
All right, thanks, Will.